physics suggests that time is not as rigid as our everyday experience might lead us to believe. In fact, according to the theory of relativity, time is intricately linked with space, forming what we call space-time. In this framework, time is more fluid, and under certain conditions, it can behave in ways that seem counterintuitive. Time travel as a concept is actually already a reality, at least in one direction. Moving forward in time is not only possible, but has been experimentally observed. The key to this lies in the concept of time dilation, a phenomenon predicted by the theory of relativity. Time dilation occurs when an object moves at a significant fraction of the speed of light, or when it is subjected to a strong gravitational field. Under these conditions, time for the object in question slows down relative to an observer who's not experiencing the same conditions. Imagine a spaceship traveling close to the speed of light. On board the ship, time would pass more slowly compared to time on Earth. A journey that lasts just a few years for the crew of the spaceship could correspond to decades or even centuries passing on Earth. Upon returning, the crew would find themselves in the future, having effectively traveled forward in time. This isn't just science fiction, it's a consequence of the fundamental laws of physics. Time dilation has been observed in numerous experiments, including those involving particles accelerated to near-light speeds and particle accelerators. These particles, which would normally decay quickly, can exist much longer than they would if they were at rest, illustrating how time for them has in fact slowed down. But what about traveling backward in time? Here, the situation becomes much more complex and speculative. The laws of physics, as we currently understand them, don't explicitly forbid backward time travel, but they do impose significant constraints that make it extremely difficult, if not impossible, to achieve. One of the most intriguing theoretical constructs that could allow for backward time travel is something you've probably heard of, the concept of a wormhole. A wormhole, often described as a bridge through space-time, could, in theory, connect two different points in space and time. If one end of a wormhole were to be moved at near-light speeds or placed in a strong gravitational field, time dilation could cause a difference in the passage of time between the two ends. This difference could potentially be exploited to allow for backward time travel. However, this idea remains purely theoretical. The existence of wormholes has never been confirmed, and even if they do exist, the practical challenges of stabilizing and traversing a wormhole are far beyond our current technological capabilities. Another speculative idea involves the concept of closed time-like curves. In the fabric of spacetime, a closed time-like curve is a path that returns to its starting point in both space and time, effectively creating a loop in time. In theory, an object following such a path could return to an earlier point in existence of closed time-like curves raises profound questions about causality, the relationship between cause and effect. If backward time travel were possible, it could lead to paradoxes, such as the famous grandfather paradox, where a time traveler could potentially prevent their own existence by altering events in the past. Resolving these paradoxes requires a deeper understanding of the nature of time and causality, which remains one of the biggest challenges in theoretical physics. The idea of using black holes for time travel has also been explored. Black holes, as I've covered in a previous video, are regions of space where gravity is so strong that not even light can escape. The immense gravitational pull of black holes cause extreme time dilation near their event horizons. In principle, a spaceship orbiting close to the event horizon could experience time passing much more slowly than in the rest of the universe. However, entering a black hole to achieve time travel would be perilous, as the immense gravitational forces would likely destroy any object that ventured too close. Another avenue of exploration involves the concept of cosmic strings, hypothetical one-dimensional defects in the fabric of space-time that could stretch across the universe. If cosmic strings exist and intersect, they could, in theory, create conditions that allow for time loops, potentially enabling backward time travel. However, like many other ideas in this domain, cosmic strings are speculative, and there is currently no experimental evidence for their existence. In addition to these more exotic ideas, there are also considerations from quantum mechanics, the branch of physics that deals with the behavior of particles on the smallest scales. Quantum mechanics introduces the concept of superposition, where particles can exist in multiple states simultaneously, and quantum entanglement, where particles can instantaneously affect each other, regardless of the distance separating them. This phenomena have led some to speculate that quantum effects could play a role in time travel, perhaps by allowing information to be transmitted across time. However, these ideas remain in the realm of speculation, as our current understanding of quantum mechanics doesn't provide a clear pathway to time travel. One of the central challenges in the study of time travel is reconciling the laws of general relativity, which governs the behavior of large objects like planets and stars, with the principles of quantum mechanics, which governs the behavior of particles on the smallest scales, as I mentioned. These two pillars of modern physics are fundamentally incompatible, and unifying them into a single theory of quantum gravity is one of the greatest challenges facing physicists today. Until such a theory is developed, our understanding of time travel will remain incomplete. While backward time travel remains a distant and speculative possibility, the implications of its feasibility are profound. If it were possible, it could open the door to new technologies and forms of communication that could revolutionize our understanding of the universe. However, it would also raise ethical and philosophical questions about the nature of time, free will, what was once considered impossible or purely theoretical can, with new discoveries and advancements in technology, become a reality. The study of time travel is not just about exploring the limits of what's possible. It's also about expanding our understanding of the fundamental nature of reality. So wrapping up, time travel as a concept straddles the line between science fiction and scientific reality. Moving forward in time is not only possible, but is a well-established consequence of the theory of relativity, observable in experiments and cosmic phenomena. Backward time travel, on the other hand, remains a tantalizing but elusive possibility, constrained by the laws of physics as we currently understand them. The study of time travel challenges our perceptions of time, space, and causality, pushing the limits of our understanding of the universe. While the practical realization of backward time travel may remain out of reach for the foreseeable future, the pursuit of knowledge in this area continues to inspire new theories, experiments, and ideas that deepen our understanding of the cosmos. As we continue to explore the mysteries of time and space, we're reminded of the boundless potential of human curiosity and the enduring quest to uncover the secrets of the universe. Time travel may not be a reality today, but the journey toward understanding